All right. Hi, everyone. So today we are going to discuss, continue our discussion on the next subtopic, which is on the Poisson distribution. All right. So class, so the Poisson distribution is another distribution or a technique that we can use when we want to find the probability of a discrete random variable. Okay, and it is used when the sample size is large and when the probability of success, which is the p, is small. And uh, to use the Poisson distribution, it is usually depends on the on the situation where independent variable occurs over a period of time or when a density of items is distributed over a given area or volume. So from this definition, you should now know already what's the difference between the Poisson distribution and also the binomial distribution. Okay, so in the binomial distribution, we have discussed that we must have, for example, fixed number of trials and there are two possible outcomes, right? But for the Poisson distribution, it is usually the number of the number of variable occurrence over a period of time or uh, when the density of items is distributed over a given area or volume. So for the Poisson probability formula, we are going to use this formula. Okay, probability of x is equal to x is equal to the um, e or exponent to the power of lambda times lambda to the power of x and uh, over x factorial. Okay, where the exponent is equal to 2.718281. All right, and it is also can be written that um, the random variable x. Okay, let's look to this. So this is a random variable x follows a Poisson distribution with mean equal to lambda. So in Poisson distribution, the lambda here is also known as the mean value for the Poisson distribution. Okay, and all right. So I think let's look at the example 13. Okay, so during a lab experiment, the average radioactive particles passing through a counter in 1 millisecond is 4. What is the probability that in a given millisecond, A, no particles enter the counter? So in this uh, situation, we want to find whether the, there is no, we want to find the probability of there is no particles enter the counter. And from the question also, if you notice that it is given that what is the probability that in a given millisecond, it means that the constraint of the for the random variable or for the radioactive particle is in milliseconds. So when reading the question, you should be able to differentiate for this type of problem, which one is better, which one is more suitable, binomial or Poisson. So uh, in this example, we cannot see that there is no fixed number of trials and there is also no like success and failure. I mean, there is no two outcomes as in the binomial distribution. Therefore, Poisson distribution is more stable for this kind of situation. So now let's try to solve the question A. No particles enter the counter. It also means that when it's no particle, it is also mean that we want to find the probability of x is equal to 0, right? So since we want to find the probability of x is equal to, when it is equal to, I think it is better for you to use the formula because in the formula, um, it is given the formula is for the equal to sign, right? So it is not much work to do here. So just use the formula. So for this one, e to the power of negative lambda. Okay, so please remember it is always negative here. And from the question, you need to first identify what is the lambda or what is the mean. Okay, so from the question, uh, the average radioactive particles passing through a counter in 1 millisecond is 4, right? So in this problem, the question also wants us to find in a given millisecond. So for this problem, the lambda is equal to 4. So for our reference, you can write lambda is equal to 4. So put it into the formula. 4 times 4 to the power of x. X is 0, right? So x is 0. So just that you know, okay, where to put it, how to put it into the formula. And for this one, maybe we want to use these values. So this is referring to the same value, which is the mean for the problem. And this is over x factorial. In our case, the x is equal to 0 factorial. Right? So you can just calculate by using the calculator. Okay, so this is the calculator here. So for this example, you may want to open two bracket first, right? And then find the first one. Okay, in the first one, okay, so where is it? Okay, shift and learn. Okay, shift and learn. So this is e to the power of negative 4, and then close it, close the bracket and open another bracket for the second one. So for this one, you can just click this, okay, x to the power of, and just key in the value 4 to the power of 0. Oops, sorry, 4 to the power of 0, and close the bracket 2 times. So everything here, why I open the bracket 2 times? Because everything that we uh, put here is for the numerator. Okay, so we group it as 1. Okay, and then you can now divide by the denominator, which is equal to the 0 factorial, shift and this one. And now you can click the equal to sign here, and the answer is 0.0183. That is the answer for the first question. Okay, now let's try B. At least four particles enter the counter. So 4 here means that probability of x greater than or equal to 4. Alright, so for this one, remember I have uh, shared with you previously uh, that we can also use the statistical table, especially when the sign is greater than or equal to. It is easier for us to use the statistical table. But if you need, the question asks you to use the formula, then you need to use the formula lah. Okay, but this time I will show you on how to find the answer by using the statistical table. Okay, all right, so now let's go to the statistical table, and you need to find the cumulative Poisson distribution. So it should be after the cumulative binomial distribution. Okay, so this is the cumulative Poisson distribution, and you have to find first the m, right? So in our case, um, m here is the actually this one is the lambda value. So please remember this one in the statistical table. M is used instead of lambda. Okay, so if you compare this formula here with our module probability of x greater than x, okay, so it is lambda x factorial. See the similarity of the two. Okay, so uh, therefore we can say that m here is equal to the lambda. So first, you need to find what is the m or the lambda value for our case. In our example, our lambda is equal to 4.0. Okay, and r here is actually the x. Okay, so we want to find the probability of x greater than or equal to 4, right? So this is the probability value 0.5665. Remember, all values in the statistical table here is always referring to the probability of x greater than or equal to any value of r stated here. Okay, so since we want to find uh, the probability of x greater than equal to 4, you can straight away write the answer that is equal to 0.5665. Okay, so go back to the module, and this is equal to 0.5665. But if the question asks you to maybe use formula, what you need to do, class, what you need to do is actually um, you need to find it manually, and it is a lot of work actually uh, by using formula. If you want to use the formula, probability of x greater than or equal to 4 for the Poisson distribution is equal 1 minus probability of x less than or equal to 3. Okay, so this is basically 1 minus probability of x greater than or equal to 0 plus probability of x equal to 1 until probability of x equal to 3. So you need to calculate all these 0, 1, 2, 3, 4. Okay, so all these manually, manual calculation, and then 1 minus everything here, then you should get the same answer, 0.5665. Okay, so that is for question B. Now let's look at question C. More than 4 particles enter the counter. So for C, more than 4 particles. It also means that we want to find the property of X greater than 4. And for discrete random variable, we have discussed before in our previous class, this is equal to greater than 4. It means that 5 and above. This is equal to property of X greater than or equal to 5. It does not include 4, but it includes 5. So again, when you see this symbol, you can refer to the statistical table. So from the statistical table, when R is equal to 5, it also means that we this value, sorry, okay, when 5, so it also means that this is the probability of X greater than or equal to 5. Okay, so the answer is 0.37, oops, 3712. So in our module, you can write the answer. It is equal to 0.3712, right? And for the last question, at most 4 particles. It means that 4 and below, right? At most 4 particles. So for D, you want to find property of X less than or equal to 4. Okay, so remember we have discussed this previously. For example, the distribution is like this: 0, 1, 2, 3, 4, 5, and so on. For Poisson, we do not have uh, uh, the value here, okay, because it is not the same as in binomial. In binomial, we have fixed number of trials, but in Poisson, we do not have that. So to find the probability when probability of X less than or equal to 4, sorry, I need to change statistical table. All right, yeah. So what you need to do is you have to, this is the probability that you want to find, right? So what you need to do is you remove everything from here. So this is basically, and we have also discussed that everything here is equal to 1. So this is to get the probability of X less than or equal to 4 here. It is basically 1 minus probability of X greater than or equal to 5. Alright, so this is equal to 1 minus, you have calculated it before in question C. So this is 0.3712. So the Answer for probability of x less than or equal to 4 is 0.6. Let's use the calculator. 1 minus 0.3712 and yeah, 6288. That's the answer. Now let's look at example 14. The number of accidents per week at a certain road intersection has a Poisson distribution with parameter 2.5. So another way of how the question can give you the information about the mean is by using the term or the word parameter. Parameter also referring to the mean value. So in this case, the lambda is equal to 2.5. Okay, now let's do the question for A. Exactly 5 accidents will occur in a week. Okay, so, oh, by the way, before that, we can also mm, rewrite the question like this. For example, a random variable x follow a Poisson distribution with lambda 2.5. Okay, for a week. So this is how we can rewrite the question in a more in a simpler form. Okay, so for A, exactly 5 accidents will occur in a week. So again, probability of x is equal to 5. Okay, so for this one, you can use the formula because it is quite straightforward to use the formula. For this one, you can write it as below times 2.5 to the power of 5. Remember, 5 is the x value over 5 factorial. Okay, now put it into the formula. Go to open two brackets. Okay, you need to first open two brackets and go to shift. Make sure when you click the shift here, the S indication is appear here and go to learn. Okay, now press negative 2.5 and then close the bracket, open another bracket, uh, then click this one, this button, 2.5 to the power of x. Our x is equal to 5. Now you can close the bracket 2 times. The first one is for the term here, only for this term, but when you close another bracket, it is meant for all term for the numerator. Okay, and we can now divide it by 5. Go to shift and click this one, 5 factorial, and click equal to, then you should get the answer 0.0668. 0.0668. Now let's go to the next question, B. At most, 5 accidents will occur in 2 weeks. Okay, when answering this kind of problem, you need to be very careful with the time, with the with the time, because the parameter or the lambda given 2.5 is for a week time, a week, 1 week only. Okay, so uh, on average, the number of accidents occur in a week is 2.5 on average. Okay, but when the time is now 2 weeks, what you need to do is you have to find a new lambda, the new mean. If 1 week, 2.5 accidents. If 2 week, 2 weeks, now you have a new lambda. Okay, so the new lambda is 2.5. I would say lambda number 2 is 2.5 times 2 weeks. So the new lambda is 5. Okay, and we want to find at most. So the probability that we want to find is probability of x less than or equal to 5. You can calculate it manually, but it requires you have to calculate probability of x is equal to 0 plus probability of x is equal to 1 until probability of x is equal to 5. This is manual calculation. You need to find everything. But for this kind of problem, I prefer to use the statistical table. So if by using statistical table, probability of x less than or equal to 5 is actually 1 minus probability of x greater than or equal to 6, right? So now you have to find the probability of x greater than or equal to 6 when lambda is equal to 5. Now let's go to the statistical table. So our lambda is now 5, right? And we want to find when r is equal to 6 or when x is greater than equal to 6. Okay, when r in the statistical table is equal to 6, it also means that the value is for the probability of x greater than or equal to 6. So which one? It is 0.3840. This is the value. Okay, now let's go back to the module. So this is equal to 1 minus 0. What was it? 0.3840. 0.3840, and the answer is 0.384. Right, 0.6160. That is the answer for question B. And for question C, less than 5 accidents will occur in 4 weeks. Okay, so in 4 weeks, again, you have to find the new lambda. So see, 4 weeks, let's say the new lambda is lambda 3, 2.5 times 4 weeks. So it is equal to 10. Okay, and the question is again, less than 5 accidents will occur. So less than 5, you want to find probability of x less than 5. How to rewrite this? Okay, this is also equal to 1 minus. Let's help you to visualize this thing. At, so we have 0, 1, 2, 3, 4, 5, and so on. So 1, 2, 3, 4, 5, 6. And this is the probability of x. So you want to find the probability of x less than 5. Less than 5, it means that it does not include 5. This is the probability of x less than 5. So everything here is 1, right? 1 minus probability of x greater than or equal to 5. Okay, so this is equal to probability of x greater than or equal to 5. Okay, now let's erase this. So 1 minus what is the probability value? Again, let's look at statistical table and find our new lambda, which is equal to 10. All right, sorry. Find m or lambda equal to 10. So this is 10 and x is greater than or equal to 5. So the value is 0.9707. Go back to our module and this is equal to 0.9707. So 1 minus 0.9707 equal to 0.0293. Right, and the last one, D, more than one accident will occur in 3 weeks. So the same thing, you just need to find um, the new lambda, but this time the number of accident or the mean number of accident that will occur in 3 weeks. 2.5 times 3 is equal to 7.5. All right. So you want to find again the problem, the more than one accident. More than one accident will occur in 3 weeks. More than one. So you want to find probability of x greater, more than one. Okay. So this is equal to probability of x greater than 2. Okay. Uh, for this one, you can use the statistical table and you will get straight answer. You will get the answer. It is easier. But if let's say the question asks you to use the formula, then what you need to do is like what I have shown earlier. What you need to do is you need to remove. So let's say this is our graph. So you want to find the probability of x greater than 2, 0, 1, 2, 3, 4, 5, 6. You want to find this is the probability of x greater than or equal to 2, whereas this is probability of x less than 2. Okay, or we can put it as x less than or equal to 1. It is the same. And everything here is equal to 1. So this is actually 1 minus probability of x less than or equal to 1, or you can rewrite it as probability of x is equal to 0 plus probability of x is equal to 1. And you have to calculate this manually, and then you will get the answer. Okay, this is by using the formula, but if you use the statistical table, of course, we can get the answer 7 point. Oh, yeah, this is interesting because 7.5 is not in the table. So in this kind of problem, it what you can do is you can use the interpolation to find the value for 7.5. Okay, you can use the value of 7.4 and 7.6 and find the middle value actually. That is by using the interpolation. And or you can also use the manual calculation. Okay, so I think for this one we will use the manual calculation because I will not show you how to do the interpolation yet. So this is basically 1 minus the 7.5 times 7.5 to the power of 0 over 0 factorial plus negative 7.5 times 7.5 to the power of 1 over 1 factorial. Okay, so for this one, the calculation is a bit long, so I would suggest that you do it one by one to avoid mistakes in the calculation. So let's proceed with the first one first. Okay, this one is negative 7.5. Close the bracket, open the bracket once again, and click on this one. Once again, 7.5 to the power of 0, and close the bracket 2 times over 0 factorial. Shift and this button. You get 0 factorial. So the value is 5.53 to the power of times 10 to the power of negative 4. So I have also shown to you this before, 5.53, right? So negative 4 means that you have to move the 0.5 to the front. 1, 2, 3, 4. So it is 0.000553. Okay, plus just change the value in the sorry, change the value, this value to 1 and 0.5 of 1. Oh, okay, 1 factorial. And for the second one is again 4.148. Then we notice that times 10 to the power of negative 3 means that you have to move the point 3 times to the front, 0.004148. So solving these, 1 minus, open the bracket, 0.000553 plus 0.004148, and the answer is 0.9953. 0.9953. So that's the answer for D. Example 14, D. Right? Now, let's proceed our discussion with example 15. All right. 8 is the average number of all tankers arriving each day at a certain port. The facilities at the port can handle at most 15 tankers per day. So in this uh, example, we know that the lambda value is equal to 8, the average number of all tankers arriving each day at a certain port. Okay, so um, additional information is also given where it is stated that the port can handle at most 15 tankers per day. So that is an additional information. Usually when additional information is given, uh, it is related with the question that will be asked. So please take note and be be careful with the additional information given. Yeah. So for the A, what is the probability that on a given day tankers have to be turned away? What does it mean that tankers have to be turned away? When we know that at the port, okay, let's say this is the port, okay, and there there is there are tankers coming in, tankers coming in, all right, and this port can only handle 15 tankers in a day. So the question is, what is the probability that on a given day tankers have to be turned away? It means that the tankers go and then it cannot enter the port. Instead, it go and it need to be turned away. When? Of course, when the number of tankers here is already 15 and the tankers that need to be turned away is when the 16 tanks and above. So, to answer the first question, it is when x is greater than or equal to 16. Okay? Or you can also rewrite this when x is greater than 15 first, because it can handle only 15. So when the 16 tank coming in, it need to be turned away. All right, so now we have the information and you can proceed with the statistical table. The mean value is 8, right? The mean value is 8. Okay. And then you want to find the probability when 16 and above tankers need to be turned away. So the value is equal to 0.0082. Go back here and the value is equal to 0.0082. That's the first question. The second one, assume that there are 24 hours in a day. Yes, it is 24 hours in a day, of course. What is the probability that there is no tanker arriving in 6 hours? Okay, so remember again, it is the same as in the previous question in example 14, but this time instead of multiplying the um, mean value, this time we need to divide the mean value. So this is the um, mean of tankers in a day or in 24 hours. So to answer question B, you need to find a new mean when it is 6 hours. So 6 hours is 1/4 of 24 hours, right? 6 over 24 is equal to 1 over 4, right? So this 1 over 4 need to be multiplied with 8, the actual mean in 24 hours. So we rewrite this 6 times 24 over 24 times 8. This is equal to 2, right? So this is the new mean that is equal to 2. So you want to find what is the probability that there is no tankers. Okay, no tankers. X is equal to 0. When it is equal to, then you can use the formula maybe. So it is negative e to the power of negative 2 times 2 to the power of x. What is x? X is 0 over 0 factorial. So let's do the calculation. Shift ln to the power of negative 2, close the bracket, open it again, click this one, 2 to the power of 0, close the bracket 2 times over 0 factorial. 0, shift this one, equal to 0.1353. That is the answer for example 15. Alright, so please be very careful with the mean number, with the time, or with the space later on. Maybe there will be examples about space. Okay, and check if you need to find the new lambda or the new mean for before you solve the problem. Okay, and always remember that additional information, this is the additional information, usually gives you tips or hint on how to answer the question. Right, now let's look at the mean and expected value, variance and standard deviation for a Poisson distribution. So for a Poisson distribution, the mean, or also known as the expected value, is equal to the lambda. Okay, so this is also the write it like this: mean or expected value. So don't get confused when maybe in quiz or in the test later on the question mention expected value instead of mean. it is the same thing. Expected value is the mean. And the variance for A Poisson distribution is also lambda, and the standard deviation for a Poisson distribution is the square root of lambda. All right. 2 point. Now, the next example is example 15. Refer to, sorry, 16. Refer to example 15 where the number of accidents. Wait. Uh, this one, it is actually example 14. Example 14. Where the number of accidents per week at a certain road intersection has a Poisson distribution with parameter 2.5. Let x be the number of accidents per week. Find the expected number of accidents per week. Find also the variance and standard deviation. So you can use what has just been given to us. The mean is equal to the lambda. Mean or the expected number of accident is equal to the lambda, which is equal to 2.5. Okay, and variance is also equal to the lambda. Oh, by the way, uh, do not forget the symbol. Okay, variance is also equal to the lambda, which is also equal to 2.5, and the standard deviation is sigma, which is equal to the uh, square root of lambda. Okay, so to find this, you need to click here, square root of lambda, which is square root of 2.5. Square root of 2.5. 2.5. This is equal to 1.5811. 1.5811. Okay, that is the answers for example 16. All right, class. Now, um, we want to look at the shape of the distribution. Okay, so um, probability of success and the shape of the binomial distribution. Okay, for any number of trials n, regardless of how many, we know that in the binomial distribution, let's recap first the four characteristics or requirement for a binomial distribution. The first one is it must have fixed number of trials. Fixed number of trials. This one is for the binomial, yeah. And number two is two possible outcomes, success or failure. Number three, independence of observation. Independence of observation or outcome. And what is number four? Um, okay, fixed probability of success. The probability of success uh, remain the same across the number of trials. Okay, so regardless of what is the number of trials? Okay, the binomial probability distribution is symmetric if P, or the probability of success, is equal to 0.5. Okay, so if you look here, when probability of success is 0.5, no matter no matter if n is equal to 4, 5, 100, um, 1000, the what if p is equal to 0.5, you will get this kind of distribution, symmetric. We call it as symmetric distribution. Okay, regardless of what is the number of trials. Number two, the binomial distribution is skewed to the right if p less than 0.5. See, if p here less than 0.5, this is example when p is 0.3. You notice the distribution now has become different. It is skewed to the right skewed. Okay, and when p here greater than 5, it is skewed to the left. Now look, when p is greater than 5, sorry, greater than 0.5, now this distribution is skewed to the left skewed. Okay, so now you know that the distribution, okay, or the skewness of the probability, the distribution differs when the probability value changes. Okay, now let's look at the Poisson. The form of Poisson distribution becomes more and more symmetric, even bell-shaped, as the mean grows larger. See the mean value here, when 0.1, it is right skewed. When the mean is equal to 2, still it is right skewed. But when mean is equal to 5, here 5, it is symmetric. So for the binomial, when p is equal to 0.5, it is symmetric here. But for Poisson distribution, when mean is equal to 5, it becomes symmetric. So having said that, um, when in the case of binomial here, in the case of binomial, if n is quite large and p is small, the condition begins to simulate the continuous space or time implication of the Poisson process. So, in other words, we can say that in certain conditions, we will discuss the condition after this. We can use Poisson distribution to approximate the binomial distribution. Okay, especially uh, the when the distribution is symmetric for both cases. Okay, symmetric. All right. So therefore, if n is large and p is close to 0, Poisson distribution can be used with mean n times p. This one is the mean for the binomial. Okay, this one. Okay, for the binomial, the mean is n times p. The variance is NPQ, and the standard deviation is the square root of NPQ. Just to recap what we have learned in our previous class, N is the number of trials, P is the probability of success, and Q is the probability of failure. Okay, so P plus Q is equal to 1. All right, now, all right. So there are conditions, like I said, okay, that can be used. I think it's better to use the highlighter. Okay, so if P is close to 1, can still use Poisson distribution to approximate binomial probabilities by interchanging what we have defined to be a success and a failure. All right. So because in the probability statistical table for the binomial, we know that the probability of success value is only up to 0.5. So when P is close to 1 or greater than 0.5, we need to change the P and the Q. Okay. So this is the approximation binomial with uh, n large and p is small, okay, can be approximated by using the Poisson distribution when the mean, actually it is when the mean is larger. So now I think we can understand better the situation by solving the example 17. Okay. So in a certain industrial facility, accidents occur frequently. It is known that the probability of an accident on any given day is 0.005, and accidents are independent of each other. Okay, so we know that now the probability of an accident in any given day is 0.005. So P here, probability of success for an accident to occur in any given day is 0.005. What is the probability that any given period of 400 days there will be an accident on one day? Okay, so we want to find in 400 days how many accidents that will occur on one day. So the question here now, the n here is the number of days. N is the number of days. All right. So in this example, you can actually find the new the mean. Okay, you can actually find the mean for this problem. So since the probability of success is small and n is large, okay, which is aligned with this one, the first condition, if n is large and p is close to 0, Poisson distribution can be used. Okay, so now with mean n times p. So in other words, what we can do is mean here can be also calculated by using n times p, and this n times p is also equal to the lambda. Okay, so in this problem, our n is 400 and the p is 0.005. Okay, so 400 times 0.005. This is equal to 2. So now the lambda or equal to the mean or equal to the mean of the binomial is equal to 2. So in this situation, you want to find the probability of, on one day in that 400 days, that will be an accident. So you can use the Poisson instead of binomial distribution. So now we will use Poisson to approximate the binomial distribution. So you want to find probability of x equal to 1, okay, which is equal to e to the power of negative 2, 2 to the power of 1 over 1 factorial. Let's try. Open the bracket 2 times, shift and on, negative 2, close the bracket, open the bracket again, 2 to the power of 1. Now you can close the bracket 2 times over 1 factorial, shift, 1 factorial. So the answer is equal to 0.2707. This is by using the Poisson distribution. Okay. So maybe you want to check if by using the binomial distribution, probability of x is equal to 1, right? So can we do it? Yes, but okay, let's try. N is 400, right? And x is 1. So probability of success is 0.005 x per 1, and um, probability of failure is 0.995 to the power of 399. So try solving this. I will do it one by one. So 400 shift C1 times, oops, really, oh, no need to shift. This is 0.005 to the power of 1. Close the bracket, oops, delete. Close the bracket, open the bracket again, 0. Oh, click this first, 0.995 to the power of 399. And enter. See, we get almost the same answer, 0.270669. So it is proven that Poisson can be used to approximate the binomial distribution, the probability for a binomial distribution when the n is large and p is very small. All right, class. So that's all for the Poisson distribution. In our next class, we will continue our discussion on 1.4, studies on the continuous probability distribution. That's all. Thank you very much.